Can you touch another universe? The question might seem strange, especially considering that in some multiverse scenarios, other universes are very far away. And yet there is one particular form of the multiverse for which this question might be relevant. I'm talking about the so-called Brane cosmology. And if this idea is correct, then it is possible that we live in a really fascinating and strange universe. Currently, theoretical physics, in some sense, is far ahead of experimental physics. What I mean is that scientists' ideas often leap far into the future and we are not yet able to test them experimentally. But that doesn't mean that they should be treated the same way as various pseudosciences, like the electric universe, which I talked about in a recent video. Scientific hypotheses and theories may sound completely unbelievable to the average person. However, unlike pseudoscience, they come with a mathematical framework, and at least a theoretical possibility to test many of these ideas, even if not right away. Brane cosmology in many ways might sound like science fiction, yet there is a certain probability that we live in such a universe, and in the future we may find out if this is true. To delve into this topic, today we'll need to talk a bit about string theories, types of multiverses, and more. So, do we really live in a four-dimensional subspace next to other universes in a vast multi-dimensional space? We'll talk about all this and more. I'm Andrei, and this is Cosmos Elementary. Recently, the word multiverse has been appearing quite often in popular culture, but I think many people, when watching such movies, just think of multiverse as many universes, without really considering the structure, the organization, where these universes are located, and so on. When scientists use this word, it is important to specify which version of the multiverse is being discussed. Let's briefly recall some versions of the multiverse. A famous cosmologist, Max Tegmark, proposes a classification with 4 levels of the multiverse. The first level of the multiverse is perhaps the easiest to grasp. Although we often say that the universe might be infinite, our observable universe is actually finite. The part of the universe that we can, in principle, see exists because our universe hasn't existed forever, and the speed of light is finite. This means that since the beginning of the universe's expansion, light has only had time to reach us from certain regions. Therefore, we live at the center of the observable universe's bubble, which is limited by the particle horizon, beyond which we cannot see anything. And for us, what lies beyond this horizon is essentially another universe. We can't reach it, we don't know what's there, but it's highly likely that the universe there just continues, with the same properties and values of physical constants as in our own universe. Other observers, if they exist beyond our observable universe, would have their own bubbles, and there would be many such bubbles, since they depend on the observer. This is the first level of the multiverse. The second level of the multiverse is trickier. Here we need to assume that there exists a hypothetical inflaton field. I recently discussed inflation in detail in a separate video. Today, one of the main hypotheses is that at the beginning of the universe there was a brief period of inflation when the universe expanded extremely rapidly for a very short time, after which it continued to expand in a more quote-unquote normal manner. The concept of the second level multiverse implies eternal inflation. In our universe, inflation ended, forming our bubble universe. However, it continues in the inflaton field, where other bubble universes can emerge. These universes are no longer merely regions of the same cosmos that are simply very far away from each other. In such universes, there can already be different conditions, different values of physical constants, and so on. The third level multiverse is based on the many worlds interpretation of quantum mechanics. Here it's all about quantum effects and the idea that in some cases, when wave function collapse occurs, new universes are created. This isn't about every decision creating a universe where you made a choice, resulting in universes with all possible outcomes. It's not that extreme, but it's still no less strange. And in the fourth level multiverse, we're not talking about bubbles in an inflaton field anymore, but about universes with not just different values of constants, but fundamentally different laws of physics, existing beyond space and time itself. In the first two cases, it is at least somewhat possible to visualize where these universes are located. In the third and fourth cases, this becomes much more difficult. And yet, another version of parallel universes in Brane cosmology allows us to at least try to imagine where these other universes are located, and even how they might interact with each other. Brane cosmology is connected to string theories, so now we need to talk about them a bit. So far, I haven't made a video dedicated solely to the string theory. Many of you are probably aware of some basic elements of string theory, like the extra dimensions and of course the strings themselves. We won't go into too much detail now, but let's recall a few things. One of the key points to understanding how the universe works is knowing what everything is made of. For example, we are made of molecules, molecules are made of atoms, atoms consist of electrons, neutrons and protons. And protons and neutrons are made of quarks. And that's about it. Well, in reality it's a bit more complex with gluons and virtual particles, but still, we don't know whether quarks are also made of even smaller parts. This is where hypotheses and theories start to emerge. String theory, or theories, is one of the attempts to describe the world at even smaller scale than quarks. In the standard model of elementary particles, particles can be considered as points. String theory, on the other hand, suggests that all particles, at a fundamental level, are one-dimensional objects similar to strings, which can vibrate at different frequencies. These vibrations, with their different properties, ultimately manifest as what we perceive as particles with different characteristics. Even more interesting is that these strings vibrate in 6 or even 7 extra dimensions. Out of context, this all sounds pretty strange, but the idea has been around for decades. It has survived 2 quote-unquote revolutions, and work on its various forms continues to this day. A logical question would be, why? Why all these complications with strings and a bunch of extra dimensions that are hard to even imagine? But in reality, there are quite a few reasons, and these reasons are very serious. If we look at the standard model of elementary particles, we have all sorts of things. Quarks, leptons, force-carrying particles, different charges, different properties, the missing graviton, and so on. But if we imagine that all of this is just manifestations of the same object, simply vibrating in different ways, it might seem much more elegant to some people. The most common answer to the question of why we need string theory is its candidacy for the role of the so-called theory of everything. Let me remind you that today there are 2 successful theories describing the universe at different scales. Quantum mechanics describes the microscopic world, while general relativity describes the large scales. But together they don't quite work. Scientists haven't yet made a quantum theory of gravity as well as the theory of everything. We haven't been able to unify all 4 fundamental forces: gravity, electromagnetism, the weak and strong nuclear forces, and also it's unclear why of these interactions gravity is the weakest. When comparing gravity to electromagnetism, it is weaker by many orders of magnitude. A well-known example is that a small magnet can easily hold a coin even though the gravitational pull of the entire planet acts on it from the other side. Such a huge difference is indeed a problem, and we'll talk about it in more detail later. String theory has been and still is considered by many a candidate that could potentially solve these problems. However, there is still no experimental evidence for string theory, and not everyone is sure that it's even possible to get them. As for such a large number of dimensions, they are required for the mathematics to work. By the way, it is worth mentioning that string theory isn't just one theory. There are actually at least 5. They are similar but different details. All of them have 10 dimensions, 1 dimension of time, and 9 spatial dimensions. 3 are familiar macroscopic dimensions, forward, backward, left, right, up and down, and 6 microscopic curled up dimensions. In 1995, Ed Witten showed that the 5 existing theories are interconnected, and they could be versions of a more fundamental form of the string theory, which has 11 dimensions, 10 spatial and 1 time dimension. and this laid the foundation for what is now known as M-theory. It's not exactly clear what the M in the theory's name stands for, but one version suggests that it stands for membrane. And branes, which I mentioned earlier, is simply a short for the word membrane. Now we've arrived at branes. Famous physicist and string theorist Brane World, in his popular science book The Hidden Reality, Parallel Universe and the Deep Laws of the Cosmos, discusses how, when he began studying string theory, he asked himself a perfectly logical question. If string theory implies a greater number of dimensions, then why are the fundamental objects themselves, strings, only one-dimensional? They have just one dimension, let's say length. Why not two-dimensional, three-dimensional, or even nine-dimensional strings? And at different times in the history of string theory, people have answered this question in various ways. In the 1980s, there were ideas about more dimensions, but when trying to describe fundamental objects with more dimensions, using the mathematical methods of the time, the mathematics didn't really work and spat out meaningless results. But now the answer would be completely different. Newer, more sophisticated objects have been discovered. Well, more accurately, they haven't been discovered yet in real experiments. However, new mathematical methods have been developed, in which fundamental objects with higher dimensions no longer led to meaningless results. And now it turns out that an object with 0 dimensions is a point, an object with 1 dimension is a string, an object with 2 dimensions, a kind of a sheet, is a membrane, which is where the term brane comes from. Then a 3-dimensional object is a 3-brane, a 5-dimensional object is a 5-brane, and so on. In this form, a string is no longer the only fundamental building block, but just one of many, specifically a 1-dimensional brane. Branes of higher dimensions can also vibrate. All of this is certainly fascinating, but one of the main problems with string theories is the lack of any experimental verification at the moment. And the difficulty here largely lies in the fact that strings in string theory are unimaginably small objects. The smaller the object we try to examine, the more energy is needed. To even detect an object like a string, we need tools such as particle accelerators, but with energies much higher than those of the Large Hadron Collider. Well, much higher. This is currently beyond our reach. However, some theories also allow for the possibility that strings do not necessarily have to be small. The energy of individual particles like quarks is small, and thus the energy of the strings, of which quarks are supposed to be manifestations, is also small. However, if the energy increases, the size could also increase. And consequently, in more modern versions, this could apply not only to strings, one-dimensional objects, but also to objects with higher dimensions. Branes can be not just large in the usual context of string theory, where large can even mean fractions of a millimeter, but actually huge. Here arises the surprising idea that our entire universe is a brane. Not just any brane, but specifically a 3-brane. After all, we live in a universe with 3 macroscopic spatial dimensions, and it essentially fills the space of our universe. As Brane World writes, then such a 3-brane can even be considered not just a 3-dimensional object located somewhere in space, but it constitutes the very foundation of space itself. Today, space is not considered to be just emptiness. Even in the most empty section of space, even if all matter were removed, fields and quantum fluctuations would still remain. So if we look at our universe as a 3-brane, it turns out that space itself is not just emptiness, but a kind of an object. Such a scenario where we live on a brane is predictably called a Brane World. And this has several interesting consequences. First, that there could be many such worlds. We'll talk more about this a bit later. Or that this view of the universe's structure could help solve one of the major problems in modern physics, which I mentioned earlier, the incredible weakness of gravity compared to other fundamental interactions. Scientists have already tried to explain the weakness of gravity by suggesting that perhaps it actually works in a higher number of dimensions, and if we consider all dimensions, it's actually stronger. But in our 3 dimensions, it appears weaker. This is how it works in the concept of Brane World as well. Firstly, to make visualizations of a 3-brane easier to understand, We need to simplify things a bit and use analogies with fewer dimensions, as is always done in such cases. It's like when the distortion of space-time as described by general relativity is visualized like this. It is depicted as a kind of a fabric which is actually three-dimensional. More correctly, the distortion of space should be depicted like this. With the three-brane, we'll do the same. We'll remove one spatial dimension and represent it as a two-dimensional object, as sort of a sheet, possibly extending infinitely in all directions. Here I've drawn it with boundaries, but again, this is for simplicity. All planets, stars and galaxies are on this sheet. Furthermore, the strings that create what we observe as different particles can be of two types. Open strings that have two ends and closed strings that form loops. Now the question arises, what should we do with the strings that have two ends? Where do they belong? The calculations show that the only place they could attach to is a brane. Moreover, it is impossible to detach these ends from the brane. That is, all the strings that through their vibrations give rise to electrons, quarks, and even particles that are carriers of fundamental interactions, such as photons and W and Z bosons. These strings can freely move across the brane, but they cannot detach from it. And that means that we, who are fundamentally made of these strings, cannot leave our Brane world. But that's open strings. And I also mentioned closed ones. Considering the properties of a hypothetical particle, the graviton, which could be the carrier particle of gravitational interaction, the strings that represent gravitons could be the only closed strings. What does that mean? It means that they are not attached to anything. Therefore, they could leave our brane. In a sense, they could leave our universe, kind of leaking into other dimensions. And considering all this, gravity is actually much stronger than what we observe on our brane in three dimensions. What we perceive only seems weaker. Yes, this is still just a hypothesis, but it isn't just some crazy idea. Everything I'm talking about follows from specific calculations. If in reality everything is truly like this, then just by simply jumping up and then inevitably returning back down to Earth due to the planet's gravity, in a certain sense, through gravity, you could feel the connection to something that exists beyond our three-brane, beyond our universe. If our three-brane exists, and if gravitons, or the loop strings responsible for gravity, can leak out, the question is, where to? Our brane can exist in even larger space, likely with higher dimensions. This place is called bulk. It's like hyperspace in which our three-dimensional subspace exists. Besides our brane, there could very well be other branes in this bulk, other universes. It is hard to grasp how two three-dimensional, possibly infinite objects could be so close together, but that's more of a limitation of our constrained brains, which aren't used to working with such concepts and dimensions. The easiest way to imagine this again is by using an analogy with fewer dimensions. Two or more two-dimensional sheets existing within three-dimensional space. In this scenario, another universe within the bulk might even be very close to us, perhaps literally just inches away. But since we're firmly attached to our brane, we can't leave ours and move to another. This definitely sounds completely crazy. The idea that another universe could be hidden somewhere right here. We can't see light from there, but through gravity, there could be some sort of interaction. And in this way, in some sense, we can touch another universe. But when we talk about different types of multiverses, it is still possible to describe where these other universes are located, even though it is hard to imagine space with higher dimensions. There's another interesting idea here. Branes within the bulk can move, and if two branes move toward each other, could they collide? And what would happen in that case? It is highly likely that such an event would be catastrophic, resulting in a massive release of energy. Can you see where I'm going with this? A powerful event on a cosmological scale? Some scientists have suggested that our Big Bang could have been the result of a collision between two branes. People often get confused by the term Big Bang and ask, what exploded? Where did the explosion happen? although the word explosion is used very loosely here, and it has nothing in common with the explosions we're familiar with. Such an idea could provide an answer to these questions. Where did the energy release came from? From the collision of branes. Where did it happen? In a higher level space, the bulk. It is possible that the colliding branes already had some structure prior to that, their own galaxies, but in the collision they were destroyed, and this marked the beginning of the new universe. Here you can naturally within the hypothesis of a cyclic universe where universes are born, die, and are reborn, repeating the cycle over and over again. There have also been ideas suggesting that this Brane World approach could potentially solve the problem of dark matter. However, the solution is quite unconventional. As many of you may remember, dark matter refers to the missing mass of the universe, which according to calculations is necessary to explain the behavior of stars in galaxies and galaxies in clusters, but which we cannot see and have yet to find. There should be more mass. It seems as it interacts through gravity, but that's about it. We can observe the effects, but we can't detect the matter or whatever it is itself. So the Brane World proposes a solution. The brain, in our two-dimensional analogy, could not just be a sheet spreading out in all directions, but it could be folded in a certain way. And stars that are far apart along the brain, through the space of higher dimensions, could be a millimeter apart from each other, and, as you remember, gravity could leak through the bulk. In other words, the hidden mass is ordinary mass, whose gravity uses shortcut through hyperspace, and it interacts gravitationally just like dark matter. Mind blown. Something similar could apply to dark energy, which is currently considered the source of the accelerated expansion of the universe. Specifically, it could help address the problem of the cosmological constant. The theory predicts a very large value, but in practice we measure a value many orders of magnitude smaller. Again, additional dimensions could help explain this. Perhaps we measure a smaller value because it is leaking into other dimensions. It's all very interesting and fascinating, but how do we test all this? The string theory related to the Brane World idea has still not been tested. Over the decades of its existence, significant progress has been made on the theoretical side. On the other hand, more and more often, phrases like string theory is at a dead end or it is incorrect can be heard. It seems that increasingly precise mathematical models have led to a tricky situation. In trying to understand how the additional dimensions might be curled, new methods have not led to a reduction in the number of candidate spaces. On the contrary, the number has increased. It is at least 10 to the power of 500. That is 1 followed by 500 zeros, more than the number of particles in the observable universe. And how can we determine which of these variants will describe our universe? And this is still just theoretical calculations, not practical testing. Still, some experimental options are being discussed, which, if not definitely confirm or refute the theory, could at least impose some constraints. For example, some Brane World scenarios are constrained by the size of extra dimensions on scales smaller than a millimeter through observations of supernova 1987A. The idea is that part of the energy from the explosion could have leaked into other dimensions. Physicists are also looking for anomalies in particle accelerator experiments. In particle collisions, it is possible to try to detect traces of graviton leakage into other dimensions. Next, such leaks could be attempted to be detected by directly measuring gravity itself. However, considering the weakness of gravity, measuring it on small scales is not easy. For example, as of 2021, the smallest scale on which the strength of gravity has been measured in an experiment is this one: the attraction between two small gold spheres with a few millimeters between them. Indirectly, some cosmological observations could help here as well. If we consider the scenario of a cyclic universe in the Brane World model and compare it with more classical scenario of the universe's evolution, theoretically, in observations, we might find traces that would support one version or the other. For example, in the standard scenario of the universe's beginning, gravitational waves could have arisen, leaving a noticeable imprint in the cosmic microwave background radiation. However, in the case of brane collisions, these traces wouldn't be present, so if they are never detected in the future, it might suggest support for the cyclic universe model. It is important to acknowledge that the idea of the Brane World, and especially the existence of other universes in higher dimensional space, remains highly speculative for now. It is undoubtedly fascinating to ponder the idea that another universe might exist just an inch away from us, separated by additional dimensions, and that there might be even a channel like gravity through which we can somehow interact with it. But we are still a long way from tests at the level of experiments that routinely confirm general relativity. However, at least these ideas are not entirely impossible. When Einstein predicted gravitational waves nearly 100 years ago, it was hard to imagine detectors like LIGO and Virgo, which now routinely register gravitational waves from events such as black hole and neutron star mergers. Back then it would have seemed impossible, but 100 years later it's already our reality. So maybe in another 100 years or 1,000, if we don't destroy ourselves first, we'll come closer to a deeper understanding of the structure of the universe. Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye!